Bose-Einstein condensation. This is a fascinating phenomenon in the field of quantum physics. In the early 20th century, Satyendra Bose and Albert Einstein together, they proposed this theory of Bose-Einstein Statistics, and according to theory, we have got Bose-Einstein condensation or Bose-Einstein condensates. Okay, so this is actually theoretical prediction. This was theoretical prediction of Satyendra Bose and Albert Einstein, and later by conducting experiment this was proved in 1995. Okay, and two physicists were awarded Nobel Prize in the year 2001 for this discovery, means actually experimental verification of Bose-Einstein statistics. Okay, so you know that bosons and fermions, only these two types of particles are there which makes the universe. Okay, bosons and fermions are there. So bosons means those are called bosonic particles and fermions are called fermionic particles. You know that fermionic particles, they obey Pauli exclusion principle, but bosonic particles or the bosons do not obey Pauli exclusion principle. What is that principle? Pauli exclusion principle. No two particles can occupy the same quantum state. That is the Pauli exclusion principle, and this principle is followed or obeyed only by fermions, like electrons, quarks. Those are fermions. But bosonic particles or bosons such as photons, then helium-4 atoms, these are bosonic particles. They do not follow or they do not obey this Pauli exclusion principle. And also you know that Bose-Einstein statistics is applicable for identical particles, and they also must be indistinguishable. Okay, and they need not to follow they must not follow Pauli exclusion principle. So these are the conditions for the particles to follow Bose-Einstein statistics. So here we are talking about, we are not discussing Bose-Einstein statistics, rather here the outcome of that theory is Bose-Einstein condensate. Bose-Einstein condensate, this is considered as the fifth state of matter. You know that four states are there, liquid, gas, solid, again plasma is there. Plasma is considered as the fourth state of matter, and this Bose-Einstein condensate, this is considered as the fifth state of matter. And the most interesting phenomena which can be observed in this case is superfluidity and coherence. Okay, so here this comes under the realm of quantum physics. Okay, and you know that in quantum physics particles behave like wave, again they behave like particles. Okay, means dual nature is observed of any quantum particle or quantum system. But in this case, Bose-Einstein condensate, okay, in this state of matter or in the fifth state of matter, dual nature is not observed. Here the dominating part which is played by the matter is only the wave-like nature. Okay, only the wave-like nature, particle-like nature remains absent in case of fifth state of matter or Bose-Einstein condensate. That is most interesting. So quantum phenomena can be studied at macroscopic level. Okay, at macroscopic level, because here coherence is observed, means you won't get properties of individual particles different. If in a system there are n number of particles, means I am talking about a bosonic system where suppose there are n number of particles, then all those n number of particles together make only one quantum system. They behave together as a single entity. That is most interesting. as a single entity, all the bosonic particles act or behave. So how this state is achieved? This state of matter is achieved at the lowest possible temperature or near the lowest possible temperature, and which is 0 Kelvin, that is known to you, or minus 273.15 degrees Celsius. That is the lowest possible temperature, and very near to that temperature this phenomenon occurs. Means Bose-Einstein condensation. This is the name of the phenomenon. This occurs nearly at absolute zero temperature. So what happens when the bosonic, say there is a bosonic system, means it is nothing but a quantum system. Suppose there is a bosonic system and somehow you are lowering the temperature of that system. So what will happen in that case? The thermal energy of the system or the bosonic particles will decrease, and the bosonic particles will move to lower energy states, because thermal energy is decreasing, because you are lowering the temperature of the bosonic system. At a critical temperature, if this way you continue decreasing the temperature of the system, then at a critical temperature, means a temperature will come. At that point, what will happen? A significant fraction of the bosonic particles will condensate, and which is known as Bose-Einstein Condensates. They together form a single entity, behaves only like waves. That means interference patterns are observed, and the property of superfluidity can be observed in that case. What is the property of superfluidity? Superfluidity means fluid will flow without viscosity. Means fluid will flow without experiencing frictional forces, means frictional resistance. Friction is nothing but resistance, a type of resistance force. It resists the motion of the fluids. But in case of superfluidity, this is nothing but a property. And the fluids which is following this property or which is having this property are called superfluids. That is known to you. Okay. So superfluidity means friction is totally absent, because all the individual particles are acting together. They are behaving like a single entity. And when there is single entity, so individual particles constituting the whole matter, they are not offering any resistance to each other. And due to this happens due to the property of coherence, which is observed at nearly 0 Kelvin temperature. So these are most interesting. Okay. And yes, applications. Scientists have already found applications of all these things. Latest technology is quantum computing. So in case of quantum computing, this fifth state of matter is used. So understanding and controlling this state of matter is crucial for the development of quantum computing. Then in case of interferometry, okay, means interferometry means you know that high level of precision measurement is there. In case of atomic clocks, so this fifth state of matter is used. Okay. Okay, yes, I have finished today's lecture on this topic. Topic was what? Bose-Einstein condensation or Bose-Einstein condensates. Okay, and this is nothing but the fifth state of matter. Applications are there, research is still going on, and this is only the state where you know that quantum mechanics, study of quantum mechanics or quantum physics, these are studied at microscopic level, but due to this property, due to this phase, a new phase, fifth phase of matter, quantum physics can be studied at macroscopic level. Okay, this is one great advantage of this state of matter. Anyway, so this was all about today's topic. So this is the end of this video. Thank you for watching this video.